Okay. Bueno, bienvenidos a todos. Es un gran honor para nuestra universidad y para nuestro departamento de geología recibir a una eminencia en la sedimentología como es el profesor Paul Myrow. Paul Myrow tiene una extensa trayectoria en las geociencias y en la sedimentología. Empezó trabajando su tesis sobre todo en el estudio del contacto entre el Precámbrico y el Cámbrico en Newfoundland, y a partir de ese momento se convirtió en uno de los especialistas en Paleozoico a escala global, y además es un entusiasta y un investigador apasionado de estructuras sedimentarias, tanto en formas de lecho actuales y fósiles. Hizo contribuciones, digamos, a escala global, que son reconocidas mundialmente. Ha trabajado prácticamente en todos los países del mundo, así que tiene un conocimiento global que es asombroso. Y bueno, lleva muchísimos años en el Colorado College. El Colorado College es una institución académica relativamente pequeña, pero que se focaliza en la altísima calidad de los egresados. O sea, es la segunda entidad en Estados Unidos con mayor calificación para sus egresados. Así que, y bueno, es actualmente el director del Colorado College. Así que bueno, tenemos el enorme placer de contar con Paul. Es autor de muchas contribuciones científicas, más de 150 contribuciones en revistas y libros de primerísimo nivel. Así que bueno, Paul, lo dejamos, tenemos acá el honor de estar en la universidad con el rector de la universidad, que justo nos viene a acompañar en esta presentación, y también el director del departamento de geología. Así que bueno, Paul, lo dejo con...
Gracias. Gracias. Gracias, Carlos. Gracias, colegas, estudiantes de Carlos, para la comida anoche, sano. Gracias, Gerardo. Gracias, director. Let's see, aprendió español, pero I will talk today in English. Better for you, better for me. Okay. Thank you. Okay. So I am a geologist and I work in the field mostly, but I'm talking about some things that I am also interested in. I work with paleontology, rocks, modern sediments, experimental, all different things. So today I'm going to talk about bed forms, and that means the shape or the form of the layer of sediment. The sediment is granular material, so it moves when you have a fluid putting stress on the sediment. And if you have a flat surface of sand and you start to move it with wind or water, it will self-organize into these structures that we see here. We see them all over the surface of the Earth. We see them on Mars. They have different sizes, different shapes. And the ones that we will talk about mostly today will be dunes, which are the large structures here, and also ripples, which are the smaller features. They are two distinct types of bed forms, and their physics is different in both cases. We see ripples today in the modern, and we can study them, we can make them in laboratories, and we can compare them to the ancient. And our understanding of what we know from the modern and from experiments will allow us to properly interpret ancient rocks. And so today I'm going to look at some experiments on these types of ripples. So I will begin by showing you the results of work done in the 1960s, 1970s, 1980s, primarily 90s, done by a very close friend of mine. He is almost 90 years old. His name is John Southard. He was at Massachusetts Institute of Technology and was an advisor and helped me with my thesis quite a bit. And what he did is he created a series of experiments that allowed him to make fields on a diagram like this, in which this is grain size, from small grains to large grains, and flow velocity from very low velocities to very high velocities. And you could see that different types of bed forms are stable in low velocities, others in high velocities, and you can use this diagram to your advantage. You go to look at a rock and you measure the grain size, you know that that grain size can have these bed forms, but not this bed form. You can also look at modern dunes, and let's say dunes, and you can say, if it's in this grain size, what is the range of velocities that those dunes are stable in? So it is used for all kinds of things, modern river studies, ancient rocks, and the idea is that you take a controlled situation, a laboratory, and you turn the velocity up to a particular level, and you look at all the different bed forms that form at different velocities. But you always have the velocity at one level. You keep it constant, and bed forms adjust to be in equilibrium with the flow. The flow is moving at a certain speed, the bed forms develop until they reach a certain size and shape, and they are constant. So this is a diagram that describes bed forms in equilibrium with the flow. I got interested in the concept of disequilibrium, and I will explain that in a second. But let me show you an example of what I mean by equilibrium. So here is the air and the water interface. So this is water, air, and this is one of these bed forms, a dune, let's say, in cross-section. So you have a flow, you turn, let's say this is an experiment, and the flow is going this way. You turn the water on at a certain level, and here you have a big cross-sectional area. Here you have a small cross-sectional area. The water is continuously moving at one rate through the system. So here, cross-sectional area is big, it will be slow. Here the cross-sectional area is small, the velocity will be fast. What that means is that the flow accelerates faster, 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 then it expands and it goes slower. And the sediment is eroded here and deposited there. That is the fundamental physics of this system. So if you have sand that is flat and you turn the flow on, these will grow and grow and grow up to a point. And they will grow no farther. And this is why. The velocity is getting faster as this grows. The velocity is getting faster, faster, faster. And then it reaches a point where the velocity is so fast that the bed form, in this case the dune, will be eroded. So it grows up to a height and no higher. At that point, everything is in equilibrium. So that is one idea of what equilibrium means. They will grow up to a height and they will stay at that height. Okay, so what I'm talking about is an interaction between topography, the flow, and the movement of sediment, right? They all are together. When you have flow, it adjusts instantly to the shape of the sand, instantaneously. If I put more sand here, the flow would go around, right? However, when you change the flow, it takes time for this to change. So the flow changes instantly to changes in topography, but the topography takes time because you need to move the sand around to redistribute and change the shape. So it's not the same. So the concept I'm talking about today is disequilibrium. Now in nature, flows are variable in time. Well, you go to a river, sometimes fast, sometimes slow. You get floods, right? Everything changes over time. But also, different parts of the river, the velocities can be different. And that is difference in space. So they are unsteady over time, and they are not uniform over space. And therefore, you would predict that most bed forms on the surface of the Earth are not in equilibrium. So we should, as sedimentologists, be talking to our students about disequilibrium. We always talk about this is what we know when things are in equilibrium. But almost always, bed forms are adjusting to changes in the flows, because the flows are always changing. And they change by moving the mass around. The mass of the sediment has to get lower, higher, change in position. So I want to talk today about disequilibrium in rivers, under waves in oceans and lakes, and aeolian on wind-blown, like the big dunes that you see in deserts, each of those. I will start with rivers, but first I want to say something about how geologists work. This is an outcrop in Australia. The layers have been tilted like this, and I see a bunch of small bed forms. Normally, I could measure the spacing of the bed forms and say something about the size of the waves if you're an oceanographer, right? You can do that. And you would assume that you could say what the waves were doing. However, if you look closely at these, there are problems. And those problems relate to the fact that the waves were not always constant. The waves were getting bigger, the waves were getting smaller, and the ripples had to adjust. And therefore, maybe if we know more about how they adjust, we can interpret the rock record much better, right? So we always assume equilibrium. However, bed forms might record transitions between one equilibrium state and another equilibrium state. Okay, so I will start by rivers. This is a river, and you can see small dunes on the bottom of the river. If we want to talk about disequilibria, this is a beautiful example, because there used to be water here. These dunes were formed by the flow of the river, but now they're exposed to air, so they are not in equilibrium with any flow, right? Okay, so these are small dunes. The flow is going this way, gentle side, steep side, right? The Stoss and the Lee. And we can do experiments and understand that in unidirectional flow, that bed forms start straight, then they get curved, and they get highly irregular, and we can apply that to the rock record. And here is Roger Walker, Carlos, who is showing how you can look at the layers cross-bedding and understand how the directions that the dunes moved and how fast the flow was, etc., etc. Okay, this is another example of disequilibrium. You had dunes that moved maybe this way, and now ripples that move this way, and now you're in air. So I think that disequilibria is the norm, in the normal in the rock record. But the best example of disequilibria in rivers is to look at the record of one flood. So this is discharge, how much water is going past the point anywhere in the river. So this is greater and greater discharge, and this is the size or the height of the dunes. And in a flood, the discharge will get stronger and stronger and stronger, the velocities will go up, and then it will turn around and go back to normal river flow. So this is what happens when you have increasing and decreasing discharge. The dunes are small. They start to merge together and grow bigger and bigger and bigger until they hit the fastest, the highest flood waters and the fastest flow. Now, if bed forms could respond instantly to changes in the water, then the dunes would go right back this way. But instead, what you see is that they grow bigger and bigger, and now the flood is going to get weaker and weaker and weaker. But the bed forms, instead of going like this, have a hard time adjusting. They stay almost the same size, and then they come back to normal flow. And this asymmetry of going like this and then like this, that is called hysteresis. It's a problem with how they behave over time. In order to understand why that happens, we can define something called the bed form turnover time. This is from an Englishman who fought in the Second World War in Northern Africa and was an incredible engineer. And what he said was that bed form turnover time is the time for a bed form to move one wavelength. So here are two bed forms. This bed form is going to be here, one wavelength. And that is the time. And it relates to the cross-sectional area. You can think of this as volume. How much sediment? Is it a big dune or a small dune? And how fast is the sand moving? Simple. It's that ratio, right? So, to think about it in concrete terms, simple terms, if you have a small ripple, it has a small volume, and it can move one spacing in seconds, in minutes, maybe a couple minutes. If this is a large dune, like you see in deserts, it could take hours to days to years. And so if you want to adjust the shape and the size, it takes a long time. These, seconds. And so that is the difference between small and large bed forms. So here is an example. I just drew this diagram for a paper that I wrote a few years ago, which illustrates this. This is velocity. And in a flood, the velocity goes up, and then the velocity goes down. And what you see is that you make ripples. They merge together to make small dunes. And the dunes get together to make large dunes. This takes seconds. This takes minutes. That takes hours. But once you have large dunes, you have to move all that mass and reorganize it back to ripples. This takes hours to days. And that is why the data I showed you looked the way it did. They got bigger and bigger, and then they had to get smaller, but it took a long time, and it took a different path on that diagram. So the point I would like to make about unidirectional flow is that ripples are small, their turnover time is small, they rapidly adjust to the flow, they reorganize quickly to changes in direction. So when you look in the rock record, Carlos, you see a set of ripples, and they're pointing this way, the flow is moving that way. But if you look at a dune and it's oriented that way, the flow could have been doing all kinds of things for a long time, and it just took too long to get it to reorganize its direction. So the orientations likely record almost equilibrium conditions. Dunes, they have a big mass, and they're often out of equilibrium. So when you go to a river and you look at dunes in rivers, the flow is changing constantly, and they're always trying to adjust to a new flow condition, but it's hard to get adjusted. So rivers are unsteady, they're not uniform, and therefore they are commonly out of equilibrium. What about different type of system? Now, Myrow, I think you will like this part, because this is about waves. These are ripples made by waves, oscillatory flow, let's say along the side of an ocean. And what you see is that the crests are generally very straight. This is a common feature of wave ripples, but you will note that there's all kinds of little problems, little cups, little holes, ripples that don't connect to each other. And in 2011, I was teaching a class in sedimentary geology at Massachusetts Institute of Technology. And I was there for a semester, and I said to my friend, is there something, can we work on something? I said, yeah. I said, look at these things. They don't look like they're perfectly in equilibrium. What is going on? What is the cause of all of these problems? And so we decided to do a set of experimental work, and I'll show you that in a second. First, let me just explain a little bit of the physics, the oceanography of how waves, ripples form. Here is the shape of a wave ripple, very pointed. The flow goes this way, and you make a vortex. Then the flow goes this way, and you make a vortex like that. And the sand gets swept up into a shape that you could call a trochoid, if you know your geometry. So, very pointy, and you can see those today in modern oceans, and you can see them in the ancient record. I was just going to say very quickly that not all of the ripples made by waves are pointy. Some are big, rounded structures like this, and if you've taken a class with Carlos, you would have learned about hummocky cross-stratification, big, round hummocks. Those are also made by waves. And when you do experiments, you realize that the hummocky bed forms are produced in tiny grain sizes, and the pointy ones are formed in coarser grain size. This is small grains, this is big grains. So you can make a diagram to interpret these features in a nice way using this diagram. That's nice. Now, a little bit about waves. If you've been surfing or body surfing on the waves, a wave comes by, you get pushed forward, and then you wind up and you suck back, and you wind up in the same place. You make a circle. And this is the path of a single water particle as a wave goes by. And that distance, that diameter, is called the orbital diameter. So in deep water, the big circles, smaller, and then down here, no movement at all. In shallow water, because of friction, those circles become ellipses, and they get flatter and flatter and flatter, and at the bottom, the water goes straight back and forth. And you call that distance the orbital diameter, even though it's not in orbit. An orbit is like the Earth going around the sun, right? It's not a circle, it's back and forth, but we still call it the orbital diameter. Okay, now, two things. There's the spacing of the ripples, which we call lambda, and then there's how far back, or how big that circle is, or how far the water goes back and forth. And you can make a plot of the spacing here, versus how far the water goes back and forth. And almost all of the ripples on Earth follow this line. And it says that the spacing of the ripples is 65% of how far back and forth the water goes. That means that if the water is going back and forth this far, then the ripples that are going to form are going to be 65% of that. That's the spacing. If they're this far apart, the ripples are going to be 65% of that spacing. Beautiful relationship that you can use to your advantage. So, I was talking to my friend and I said, why aren't the crests straight? Are these because of disequilibrium? So he and I built an experimental apparatus in this building using whatever spare parts were laying around on the ground, chewing gum, just, nailing things together. No money at all. We had no money. We just put it together using the leftovers. And it's about 7 meters long. It's 60 centimeters wide, 50 centimeters deep. And we built this. We have on this end here a motor with an arm and off-center, so it goes like this, and it makes a paddle that makes a wave. The wave goes across, it comes to this end, and we put rubber, and it kills the waves. We hope it kills the waves. Mostly, not perfectly. Okay, now we put a camera up here, and we take a photograph every 30 seconds for 20 hours. 30 seconds for 20, lots of photographs. And then we use that as our data. So here it is working with the paddle on one side, the board, and then the wave coming across. We have sand on the bottom, and we generate ripples, and we study those ripples. So this is what it looks like when you are looking at the waves going back and forth. Vortex, vortex, vortex on the other side. And you can see the sand is basically swept and swept, back and forth. Okay, so we start by take a rake, a Zen rake, like in Japan, the gardens, the beautiful gardens, and we make this in here, like that. And then we start and we make the ripples, and we want to see, we make the ripples and they become in equilibrium with the size of the waves that we create by choosing the motor speed. Motor is going a certain speed. Okay, so then we're going to change the motor and we're going to make disequilibrium, and I'll show you what that means. I'll just show you quickly a little bit of this movie showing how the raked sand is becoming ripples, and that those ripples will have a spacing that is appropriate for the size of the waves that are making those ripples. Okay, so here is our experiment. We set the motor to a certain speed, we make waves of a certain height, and they will make, that will create a certain orbital diameter. And then we let it go for 12 hours until the sand and the waves are in equilibrium. The ripples will quickly develop a particular spacing. We get to here, and then we stop, we change the motor speed, maybe to bigger waves with bigger orbital diameters. And then we keep going, and then you can see that the ripples adjust to a new spacing. And it is in here that they always say all hell breaks loose, like the craziness happens. Okay, so here's some data. This is wave periods, but you can think of this as time. Time this way, 20,000 waves, 10,000 waves, 20,000 waves. And this is the wavelength, or the spacing of the ripples. So they quickly, over 3 hours, 4 hours, develop into stable conditions. Then we stop, we change the motor, and then it takes time because you're moving the sand around and reorganizing the bed. It takes time, and eventually they get to the new equilibrium. Equilibrium 1, equilibrium 2, disequilibrium. Okay, now, if all of the crests are perfectly straight, like this, perfectly straight, you would say it has essentially no entropy. There's no disorder. This green is a measure of disorder, how perfectly organized those crests are. And so here the entropy is low, but as soon as you change the motor, the entropy goes up because the whole bed changes its orientations, and then it starts to organize and the entropy goes down and you have straight crests again. Let me show you some examples. But before I do, I want to say one more thing. The point of this exercise is to look at how you have a certain spacing, let's say this spacing, and you want to have smaller spacing. You change the motor. Or if you have smaller spacing, you want to have larger spacing. So if this is a certain area, you can count the number of crests. You can do the same up here. You realize very quickly that you have to get rid of destroyed crests. To go from here to there, you have to make crests. So nobody had ever done these experiments like this to find out how do you go from this to this, or how do you go from that to that. So I will show you how it happens. And the point is, when it happens, all kinds of defects form. These are problem structures that don't look normal, and they develop and they live for a little while and then they go away. So they are short-lived. And they record a transition from one equilibrium to another equilibrium. And the type of defects depend on whether you are making more crests or less crests. Okay? So I'll show you both examples. Oh, wow, they're most beautiful. Okay, so I am going to show you a movie where we turn the motor on, we leave it on for 12 hours, and we make equilibrium. Then we're going to see the movie stops, and you'll see a person leaning over, and then we change the motor, and then we're going to see that the crests are going to develop. Oh, look at that. That's incredible. And they are very well spaced, right? Depending on the orbital diameter. And then we stop, we change the orbital diameter to be smaller waves, smaller orbital diameters, and therefore more crests closely spaced. So we're shortening the spacing. And it'll happen in about 5 seconds here. All good? And now, watch these ripples. They become like this, hourglasses, and you see new ripples forming between the other two ripples. They grow up to be the same size. And now you have 2 times the number. That is beautiful. Now I'm gonna move it forward so you can see like that, but I'm gonna go back here and I'm gonna find the space and I'm gonna just move it quickly. Watch. You see the ripples become irregular, and you see the smaller new ones, and then they grow big. Look at that. And they double the number. Oh my God. We were so happy. It was very exciting for us. So when you do that, you create odd structures like these things we call cups, tazas. And then we have these new ripples that are forming between the older ones. They grow up. And so this is the record of going from widely spaced to closely spaced. Now, here's a different problem. They're closely spaced, and then they're going to be widely spaced. That means you have to get rid of crests. And so I'm going to skip the first half of the movie. And I'm just going to show you, we changed the motor, and now it's going to go, okay? So what we're saying here is that the crests break into little fragments, and then they get reorganized into wider spaced ripples. 1 second in the movie is 10 minutes. 10 minutes. Fragments, and then reorganization. Okay, so I can do the same. Whoops, I'll go back, I'll go forward, whoops. I'll do this again, and now I'll grab this thing and I'll go quickly. They're small, Good Lord. Oh, good Lord. Like that. And when you do that, you get different types of structures. They break into pieces, and we call them zigzags. And you can find all these things in the rock record. Well, if you know how it works in an experiment, you can apply it to the rock record. That's what we're trying to do. I want to mention two types of patterns that lasted longer than all the other defects. All the other defects are gone. There are two that are very difficult to get rid of. One of them is bifurcations. So a tenedor, a fork, right? Two fork, meaning that one crest breaks into two parts. Bi, two, fork. And this is an example here. They're very hard to get rid of, because I think when I look at this field, there are some that are forking this way, and then some that are forking this way, and overall, they sort of allow each other to survive. One do this, do that, and they all sort of work out one way or another. And now, I'll show you a movie of another thing called edge dislocation. Anybody here a mineralogist? Okay, so when you make a crystal, sometimes the crystal is formed by a structure, right? A lattice. They call it a lattice. And if you have a little problem in the growing crystal, crystals can move the problem all the way to the edge and it's gone. You can see this. Physicists have imaged this, and they can see how the crystal gets rid of the problem. The problem here is this. You have straight crest, pretty nice, but over here you have an extra crest, an extra crest. So what I'm saying is that ripples get rid of the problem the same way. They move this problem all the way to the edge and out the system. So when I was a student, it was in the phase when students loved cinema. They liked art film from Europe. Difficult, long, boring, weird films, and we all just loved films. And we were always told, the greatest film ever made is Lawrence of Arabia. Oh, it's the great film. But I think that this one right here could be even better. Wait till you see this film. Watch. Spectacular. And one more. I think that deserves another watch. Okay, watch again. And now, perfectly aligned.
You didn't see that in Lawrence of Arabia?
No.
It happens over there.
Yeah, exactly. This is much better. And here's an old rock from Australia. And you see the straight crest here, but then you see the extra pieces. And I think this is capturing that change, that instability because of disequilibrium. So these are photographs I took at different stages showing that you go from small to large spacing and the types of features. A little bit of shortening and it goes through this. A lot of shortening and it takes this path. So if you can look at these patterns and understand them, you can use them as a geologist or as a sedimentologist working in the modern. And we finish this work by showing a phase diagram, we would say, right? It is a diagram that this is time, and on this axis is the percent of lengthening. This is 0%, lengthening, 20% wider, 40% wider, 60% wider spacing, or smaller spacing, 20%, 40% to 60%. And you can see all of the different structures that illustrate what happens when you do a little bit of shortening, a lot of shortening, a little bit or a lot of lengthening. And so all of these features develop and then they go away. And the last two things you have, or three things, are bifurcations, edge dislocations. And if you ran it way into the future, maybe, and you kept the flow perfect, you might get rid of all of them, and all of the crests would be parallel. So, all of that is about how ripples, wave ripples, adjust. The other question is, how long does it take? So, wave ripples have small sediment volumes. And according to Bagnold, if you have small volumes, it's a very small turnover time, so it should happen quickly. But unfortunately, the water is going back and forth. So you are trying to move sand around, but it's not all moving in one direction, it's moving back and forth, and therefore it takes a long time. It takes hours for these ripples to adjust. And there are two things that make the adjustment faster. One is if the total bed shear stress or the velocity is high. Okay, so all that means is that if you have a bunch of ripples and the velocity is slow, it takes a long time to move the sand. If the velocity is high, then the sand moves more vigorously back and forth, and you can adjust faster. The second is that we did not think of, and it was very interesting for us, the number of initial defects. Okay, so I will explain that with some pictures. So we set up the experiment, we leave it for 12 hours, we came in the morning, and look how beautiful and perfect that is. No defects. Then we changed the motor, and off it goes, and the spacing was going to increase, but look, it took 20,000 waves to get to a new spacing. Here's the other thing we did. We come in the morning, and it looked like that. It was in equilibrium, almost. But we've been sitting here for 12 hours, and we're like, forget it. Let's change the motor. What we found is that if you change the motor, and there are a number of defects in the field already, it changed within 5,000. So if you have a perfectly straight orientations, it's hard to get the sand to move. If you have a bunch of problems, defects, then you have accelerations in different directions, and that allows the sand to move more quickly. So this was all fun and interesting for us. And we started by looking at what these features are in the modern, and then we found a bunch of experiments, and we saw that the experiments could be found in the ancient, like this, or in the modern, like this, are experiments we are now using to interpret both modern ripples and ancient ripples. We're going to end with a quick discussion of aeolian bed forms and think about disequilibria in aeolian wind-blown environments. We have beautiful dunes of different sizes and shapes on Earth, and we have beautiful dunes on Mars. Mars is covered with sand dunes, and you can see that both on Mars and on Earth, you have dunes, and then you have smaller ripples on the backs of the dunes. So, in unidirectional flow, we were able to say, you find a ripple, this is the conditions. Here's a dune, these are the conditions. So there's a stability diagram that was used for unidirectional flows. There is no such thing, no equilibrium bed form diagram for aeolian deposits. Dunes in the aeolian don't work that way. So, why is that? In the aeolian, you have ripples and you have dunes, and they're two completely different sizes. Aeolian ripples are very, very, very small, a couple of millimeters high. The dunes have a minimum wavelength of 10 meters. Big, huge difference in the size of the two bed forms. This is what it looks like. These are the dunes, and these are the small ripples. They are very small, they have very low volume, therefore they can reorganize like that, instantly, like seconds. 20 seconds, you can move a whole ripple. So So what we realize is that for a dune field, the pattern is organizing all the time. Dunes are moving around, the ripples are moving around, they change the height, the length, the shape, and we believe that aeolian dunes are never in equilibrium with the wind. Remember I told you before that in dunes in a river grow until they are 30% of the depth, and then they stop growing. They are in equilibrium. In a desert, the flow goes all the way up to the top of the atmosphere. So those dunes will never grow up to the point that they can't grow any higher. So no problem, they are always evolving. So you cannot use the size of the dunes to really say almost anything about the paleo flow. It's very hard, it's very difficult to do that. We do know, in other people's work, one of my students wrote this paper, that they are moving, they are converging, and then they're breaking apart, and they're constantly moving. It's a very dynamic system. Now, with that in mind, you say, well, how long does it take for dunes to adjust? The dunes, this is a place in New Mexico, the state of New Mexico, just south of Colorado where I live. And the spacings are 100 meters. We have LiDAR surveys, the surveys of the dunes, and they migrate 2 meters a year. Their spacing is 100 meters. So to go one wavelength takes 50 years. And think about 50 years. If you stood on a dune for 50 years. Okay, is that every day the wind is changing. It's changing constantly. Direction, magnitude, big winds, small winds, and the movement of the dunes is the sum of all of those various changes. So if you want to think about equilibrium for dunes, you might have to think of equilibrium with the wind over like time scales of climate. But climate's changing too. So maybe nothing ever happens because it's highly unsteady wind and not uniform from one place to the other. It is not consistent. So if you ever work in the rock record and you see a wind ripple, you can say, though, if it was oriented this way, you say, that's the direction the wind was blowing. But if you see a dune in the rock record, the wind was blowing, every couple months it could shift to another direction, and every day it can change directions. So they're almost always in this equilibrium. Overall conclusions. In the geologic literature, you look and you see that people interpret bed forms based on equilibrium relationships. However, disequilibrium is critical for understanding the physics and the interpretation of rocks in the ancient and in the modern. How they adjust to different sizes and shapes depends on the type of flow. Was the flow one direction? Was it a wave? Was it winds going in different directions? We know that small bed forms have small volumes, and they probably are telling you exactly what was going on at the time that they formed. You see a ripple in the rock record, it's tiny, the water was going that direction for sure. But bigger structures, not as useful. So the point I think I would like to make is that you can have a more sophisticated interpretation of modern dunes and ripples, ancient dunes and ripples, if you're thinking about disequilibria. And you have a potential for a much more modern approach to teaching bed forms in classes, in the universities, and looking at the rock record if you're thinking all the time about how ripples and dunes are changing their shape and size over time. Thank you very much.
Thank you all for excellent speech.
Thank you. I am happy to answer questions.
Yeah, we have time for some questions.
Oh, the physicist.
Yes. Beautiful thought.
Thank you so much.
Well, I have one.
Thank you very much.
Wait, here.
Well,
No,
I
You
have
can
one.
start.
I will start.
You have to leave. You have to leave.
I'm sorry for my rusty English. But pattern formation appears in different systems in nature with wavelength selectivity. There is a beautiful paper by Kiel
Yes.
that employs the ideas of phase transitions to understand
Yes.
how the title of the paper was When Symmetry Breaks, How Big Are the Pieces?
Ah, that's beautiful.
They were trying to understand how are distributed the defects in the universe.
Oh, really?
Topological pancakes or some kind of weird defects that appears in the universe. But these same ideas were applied also to crystals, liquid helium, and even in these systems.
Yes.
A system that develops stripes. And I think many of your experiments could be compared with the predictions of field theory.
Now I want to read that paper.
I will send you the page.
Okay, send it to him and he will.
Yes.
He will.
Another beautiful paper that collapsed the main ideas of pattern formation systems is a paper in Science describing the main equations during a phase transition that you showed. Yes, and they also show how dislocations and discriminations appears in the system.
You have a very smart president of the
Very, we are very proud.
Wow. Thank you so much.
Another interesting point about the stripes.
Yeah.
An Argentinian policeman discovered or used by the first time in forensic science the fingerprints.
Oh, right.
Yes. Vucetich applied the fingerprints by the first time to identify murderer. Long time ago. And in order to identify people, the key are the defects. If you have a perfect pattern without defects, you will not find.
You will not. That's true. That's true. Everybody has the same. You cannot start your computer.
I'm sorry for bothering you.
No. Oh, that's great.
I love this topic.
Oh, great. Thank you so much.
Thank you. I must leave as well.
Okay. Gracias. Gracias. Thank you again. All right. Yes. Okay.
Buen fin de semana.
Uh-oh. You cannot leave. You are not allowed.
Good way to get the money.
You have to pay. You want to pay?
How much are you going to pay?
Yeah. We have another question here from Cynthia.
Okay, I'm Cynthia, because I'm a meteorologist.
Yes.
And I have a question when you talk about the dunes.
Yes.
Usually, any region has a predominant or prevailing wind.
Yes.
Then I know all the turbulence and I know that the wind changes the direction, but usually there are a prevailing wind direction. You find in the patterns of the dunes that, you know, the crests have in every region.
Have a certain direction.
They
Yes.
have some direction usually that in a way indicates what is the prevailing winds.
Yes. Yes. So the prevail usually if they are aligned, that means the prevailing winds. If you have average all the winds for a year, your prevailing wind would be that way, and they orient themselves like this. But there are also places where the wind shifts regularly at an angle, and then you get those star-shaped dunes. So if you have winter winds from one direction, summer winds from another direction, sometimes you get linear dunes that the wind is going this way, the wind's going that way, and you wind up with a strip like this. So the geometries are very difficult to interpret because you're looking at the sun the sum total of all the wind transport of the sand. I will say one thing that I could have talked about and I think is very fascinating. There is a type of equilibrium in aeolian dunes. So you know when you look at the Earth, there's only a few places where you have deserts. Now the whole Earth isn't covered with deserts. They have to be just in the right places. Some are big, some are small, but there's not that much of the Earth covered. And one of the reasons is that you have to have just the right amount of wind. And so this is a type of equilibrium. And the amount of wind is this. You want to make a desert. You have to have enough force, shear stress, of the wind to move the grains. So when you teach sedimentology, you probably talk about Shield's diagram. You have to have a minimum amount of force to move the grain. It's the force to move against the weight, the gravity pulling on the weight of the grain. So you have to exceed the minimum, which is called the critical shear stress. So the winds have to be faster than the critical, the minimum, to move them. However, if they are more than 1.5 times critical shear stress, instead of the grains going up and falling and moving across the dune field, 1.5 times or more, they get picked up, but they don't fall. They go way up in the atmosphere, and they are carried across the globe. And they could wind up in Chile, right? Another country, very far away. And in that case, if the winds are regularly more than 1.5 times critical, all the sand gets taken and is removed, and you no longer have a dune field. So you will not have dune fields unless you have winds strong enough to move the sand there, but they can't be too strong that the wind picks them up and takes them far away. So there is a sort of equilibrium, sort of window of shear stresses where you can have a dune field. That's a sort of another way to think about equilibrium. Any of those chicos? Yeah.
Hello, yes, my name is Camila, and I have a question about are laboratory studies being conducted with colonized sediments or something like binders used to simulate the effect of extracellular polymeric substance produced by microbial activity?
Yes. Okay, that is a beautiful topic. And I have a friend a colleague at MIT who is a sort of halfway between biology and geology, and she ran a number of experiments with waves, and she showed that if you had EPS in between this polymer of organic material in between the grains, the shear stress has to go way up. But then you get to a point where you break the surface, and now you can get underneath. You create turbulence, and it starts to go underneath, and then the pieces break off, and then at some point the whole floor becomes full of pieces of the microbial mat, and the microbial mat is like moved around as chunks along the floor. I can give you the reference for those papers. It's a beautiful study. Very interesting to think about.
Well, actually, with Camila, we are working on those microbial mats and doing those kind of things.
Oh,
With measure currents with that.
wow.
That's part of
That
it.
is.
I know why the question from them. Yeah, and my question is, I have another disequilibrium, because what you showed, that was beautiful, all the experiments and all things you did. But when you get to the real place or real beach,
Yes.
you randomly, very rare, you have a monochromatic wave like you did in your
Yes.
and then you don't have a flat surface. You always have a slope. So those kind of things are creating another disequilibrium. You get in the beach.
Yep.
Very, very similar structures that you you are showing, and we are trying to study them with a specific structure we build on that. But the point is that you have a lot of I would say asymmetric ripples on the beach that are responding to this kind of changes in the wave conditions and the different periods and different heights that you will see on the beach. So this is another disequilibrium.
Oh yes,
that's very important to consider when you are moving to the geological record.
That's right. I totally agree. I mean, I guess my one point I was trying to make is that that in these controlled experiments, you can have this is the best way to understand how things are going. But in nature, never, because you have wave trains, and you have groups of waves that are different sizes, and if you're a surfer, you know that sometimes you get big waves, you just wait a few minutes, so the waves are not the same size, and the topography is different. So now you have form roughness. You have the shape that is causing accelerations and decelerations in the flow just because of the shape. You have bed form roughness, which are the small things, but then you have larger scale ups and downs that is going to accelerate and decelerate. And then when you look in modern, you see that the spacings go like this. You know, the ripples get smaller, spaced up onto a little mound, and then they get wider. And then you have accelerations that are not just back and forth, but along the length, and it turns into a big mess.
Exactly.
It comes into a big mess.
That was amazing.
Yeah, this is amazing. Yeah. Chicos, ¿preguntas? Por favor. You are shy.
Pueden hacerlo en castellano si quieren.
Sí.
Se lo traducimos.
No problem. Okay. Well, I am happy to talk with you afterwards if you would like. Okay. Thank you so much.
I have one question. One or two questions.
He was like, okay, now we
I want to go. I want to go.
He considers himself a chico.
Oh, yes, Chico. Yes. Okay, Chico.
I was always fascinated with the Aeolian system because at present, as far as I know, we don't have any basin actually with the accumulation of Aeolian deposit in the geological record.
Yes.
Most of Aeolian systems are located in areas in which you have perhaps some erosion, long-term erosion, because you don't have, or you only have some little subsidence, like the Gobi or Sahara.
Yes. This is a major problem because in the western U.S., you have deposits that are hundreds and hundreds of meters thick of Aeolian sand.
Yeah.
And normally the sand should, like in the Sahara, the sand just goes right into the ocean, right? Just across the flat surface and going back. But you need to pile it up. And how do you pile it up? There either you make a hole and it goes into a hole, right? Subsidence.
Mm-hmm.
Or you have spatial deceleration. So that here are a bunch of dunes moving like this. But if you have the dunes in front going slower and the ones behind going faster, they will pile up on top of each other. Right? That is, and they will climb. That is bed form climb for you sedimentologists. They come up and they climb up the back of the other one and they pile up. So you have if you have a system like we have in Colorado, we have a sand dune national park, and there's a mountain, and the wind comes across, it hits the mountain, and it slows down, and the dunes go to the mountain and they stop, and all the dunes behind climb up the back of the other one, and they're piling into a big pile. But when you look at the continental scale, it's hard to imagine how you get 500 meters of aeolian deposits over the entirety of Colorado, Utah, and Nevada. Very, three big states. Very hard to do. I don't understand it, honestly.
Okay.
In Catamarca, we have a dune 700 meters high that is piled up like this.
Yeah. But my question was because many deserts are located in areas that lack of any subsidence.
Yeah.
So you are not going to preserve this in the geological record.
Exactly. It will all just go right back.
This always is going to move somewhere.
You have to, yeah. In that case, it has to be spatial deceleration.
Yeah.
Only answer.
More questions? Okay. Thank you, Paul.
Thank you.